Okay, so in number 23 of section 3.1, it says that we should locate the absolute extrema of the function on the closed interval. Our function is y equals 3 to a 2/3, or excuse me, 3 times x to a 2/3. This 3 is not associated with that base. If it was, we would see something that looks like grouping symbols around it like that. But we don't have that, so this 2/3 is only associated with that x. Minus 2x on the interval, -1 to 1. So we're trying to find the absolute maximum and absolute minimum that occur on this interval. Now, one thing that we have to try and figure out is where this function is continuous, right? So we are taking a cube root, and a cube root is defined for all negative and all positive values, so that's good. And this is just 2x, that's a continuous thing, right? So we do have continuity with this function. So since we have continuity with this function, we can assume that it is continuous on an interval from -1 to +1. So that's good. The next part is to take a look at, cannot be added, that's fine. So the first part is to find a derivative and collect up all of the critical points, because our extrema can only occur either at the endpoints, so we have the endpoints, -1 and 1, right? End point, and another end point, and our function on -1, so -1 to a 2/3, we're going to square it, which makes it positive, and then we take a cube root of 1, so that will just be 1, so we're okay there. I'm sorry, 1 for that, so that will be 1 times 3 minus 2. Oh, so it is 1. So that's good. And then at 1, it's going to be... I'm sorry. And then that's... -1 goes into this, so it's actually +2, right? So it's 3 times -1 to a 2/3 minus 2 times -1. So it will be 3 times 1 plus 2. So this will be 3, 4, 5, 5. So this endpoint is 5. The other endpoint here for x equal to 1 is 3 times 1 to a 2/3. That one's much easier. That's just 1. Minus 2 times 1, so that is 1. 1. Okay, so that's what our values of our endpoints are. Let's try and find some critical numbers here. So let's see. We can use the general power rule. We take the 3, bring down this 2/3, and multiply by, we can reduce this power by 1, and this is going to give us to a -1/3, and then the derivative of -2x is just -2. Simplify, we get a 3 that cancels here, so we can take this negative exponent and bring it down into the denominator of the fraction, and this is where that part comes in, because I have noticed that some students will take the 2 or whatever the coefficient of this is and also send it down into the denominator. No, it's whatever the base of this exponent is, and that's what gets sent down into the denominator. So this is 2 over the cube root of x, or x to a 1/3, minus 2. So our other critical numbers are wherever the derivative is either equal to 0 or that it does not exist. Well, the derivative can exist, obviously, at x equal to 0. Y prime does not exist. The reason for that is we get division by 0 here. Division by 0. Right? So that would indicate that the derivative probably doesn't exist at this point of 0. And 0 gets smack dab right in between -1 and 1. So this is a critical point. What's the value of my function here? So this is y, this is x. We have the endpoint here. We have this other endpoint that's right here. And we have this critical point of 0 so far. So what's the value of my function there? That's going to be 3 times 0 minus 2a. 2/3 minus 2 times 0. Hey, that's just 0. Okay. So then, what about for other values? Where is y prime equal to 0 to find the other critical points, if there are any? Well, that's wherever 2 over x to a 1/3 minus 2, wherever that is equal to 0. So we can just solve this. Let's add 2 to both sides to get rid of this -2 here. Send it over to the other side. And that's still to a 1/3 equals 2. We can multiply both sides by x to a 1/3. So this gives me 2 equals 2x to a 1/3. Divide by 2. 1 equals x to a 1/3. And therefore x. You can raise both sides to a power of 3 here to get rid of that rational exponent. So 3 times 1/3 just gives me x to a first power, which is just x. And then that is equal to 1, because 1 cubed is just 1. So our one endpoint here also happens to be a critical point. So that's fine, we were checking it anyway. So our absolute max and our absolute min can only occur at these 3 points. So this would tell me that, just looking at it, turn on this red layer again, that this point would have to be my absolute max on this interval of -1 to 1. And this point right here would have to be my absolute min on this interval from -1 to 1. So my absolute max occurs at x equals to -1. And that value is 5. My absolute min, another way of saying that is global min or global max on an interval, is 0. And that occurs at x equal to 0. And note that we wouldn't have found that if we didn't look at where our derivative did not exist. So if we plot this bad boy, keeping in mind that with these rational roots on some graphing calculators, times x, you want to make sure that only positive numbers go into some of these rational roots, because some graphing calculators use logs, like we covered in the last video for problem number 13 or 5? Oh, problem number 5 of this section. So minus 2 times x. Right, and we take a look at this, right? So here we can see that we get this very rapid change in the rate of change right at x equal to 0, right? It looks like it comes down and then suddenly it veers direction, right? And then has a positive rate of change over here. So at x equal to 1, right? Our interval is from -1 to +1. We have a minimum that occurs right around here, and that's a y value of 0. And it is clear that our absolute value does occur at x equal to -1. It's very clearly the highest value on this interval. If we look at this from instead of negative 10 to 10. And instead we go from negative 1 to 1. There we go. You can see that our absolute max for this interval of negative 1 to 1 occurs at the left endpoint over here. The minimum value occurs at x equal to 0. And that is problem number 23.